Very good afternoon to all of our students. Welcome to another edition of CEC Gurukul lectures. As we had continued discussing counters since last time, we had seen that counters are of two types depending on their modes, how they work. They were asynchronous and synchronous in nature. And after that, we had seen that counters could be count up counter or count down counters. So right now, we begin by introducing some element of artificial intelligence into the counters. The same hardware can be used as a memory element as well as to count up or count down. So looking at the circuit that we have here, today we are going to discuss our lesson based on controlled count, and for this we have the controlled counters. As you can see, we have J and K flip-flops. We have in fact 4 J and K flip-flops. That means we are going to discuss 4-bit counting. In this 4-bit counting, for each bit we have one flip-flop. Now looking at the circuit, we find that the inputs, that is the J and the K of each flip-flop, is connected to an AND gate. We also understand that for an AND gate to give a high output, all of its inputs should be high. Otherwise, the AND gate output would always be 0. So, it is important to note that clocking of all the flip-flops is done through the same clock. That means this is a synchronous circuit. Initially, we can also see that there is an active low clear signal that is affixed or connected to all the flip-flops. Going a bit back, we know that active low helps us get the signal strength same in all the circuits, because all the circuits may have a different high level, but their ground level is always 0 volt. So looking at this circuit, we initially clear out all the contents of the flip-flops. After that, the high signal that we have can be either 0 or 1. Till the time the high signal is 0, then values of all the flip-flops, that is J0, K0, J1, K1, J2, K2, J3, K3 is 0, 0. That means from the truth table of JK flip-flop, we understand that it retains the last state. Hence, the flip-flops till the time the high value is 0 gives or retains the last state and hence behaves as a memory element. The counting starts only when we have the high state going to 1, 1. That is J0, K0 equal to 1, J1, K1 equal to 1, J2, K2 equal to 1 and J3, K3 also equal to 1. With the J and K values at 1, we find that it is always the complement of the last state and hence the counting. So looking at the LSB flip-flop, which is the rightmost of your screen, we initially give a high clock. We have J0, K0 as equal to 1. Then as we had cleared the flip-flops, the outputs, that is Q0, Q1, Q2, Q3, or rather if I may go from MSB towards LSB, Q3, Q2, Q1, Q0 had the values 0, 0, 0, 0. At the first clock pulse, when J0, K0 is high, we will have Q0 changing its value to 1. However, since it changes its value to 1, however, its output is connected to the AND gate, and that AND gate still gives a value of 0. Hence, after the first clock pulse, we get the output Q3, Q2, Q1, Q0 as 0, 0, 0, 1. That is 0, 0, 1. In the next case, when the second clock pulse comes, then again the value of Q0 changes to 0. From it had 1, now it changes to 0. Now the value of Q1, which was 0, now changes to 1, and Q3 and Q2 retain their values. So next counting output would be Q3, Q2, Q1, Q0 equal to 0, 0, 1, 0. Alright. So here it is important to note that only when we have a rising edge does the flip-flop change its value, and this way till the time when we have kept all the inputs of each flip-flop, that is J and K, both at equal to 1, they will start counting, and hence this is the diagram of a 4-bit controlled counter. Synchronous counting we have already discussed the last time, and hence we are not repeating. The important thing to note over here was that in the synchronous counter we have been able to introduce a bit of artificial intelligence by means of the signal high, wherein if we keep high signal at 0, this behaves as a memory element, and when the signal is kept at 1, then it starts or behaves as a counter. Now we move to another category of counters, which are the ring counters. So in counting, sometimes we have to use or rather address some memory locations. For this, ring counters are used. So what are ring counters? Ring counters are the counters which, instead of counting with binary numbers, we have only a particular word which is controlled through a single high bit. It is more clear looking at the circuit which is now shown on your screen. Again, we have taken the case of 4 bits, wherein besides the LSB, all are connected to the active low clear. The LSB is connected to a preset, which again, as we have discussed earlier, that the preset signal is used, or preset terminal is used to feed in a particular data to the flip-flop, whereas clear signal is used to clear out all the data from the flip-flop. So for the 3 flip-flops besides the LSB, it is the active low clear. However, for the LSB flip-flop, least significant bit flip-flop, we have the clear signal acting as the preset. So initially we clear out all the flip-flops by writing in 0, 0, 0, 0. Even for the LSB we write in 0, but for other 3 flip-flops we clear the contents. So effectively it goes 0, Q3, Q2, Q1, Q0 goes 0, 0, 0, 0. Now what we do, we note that in this case also it is a case of synchronized counting, because all the clocks are tied to one another, right? And no previous flip-flop is not clocking the next flip-flop. It is simultaneous. Now what happens is, after we have Q3, Q2, Q1, Q0 as 0, 0, 0, 0, we preset the LSB with a 1. After that the clear signal goes low, and hence at the next clock pulse we would have the reading as Q3, Q2, Q1, Q0 would read as 0, 0, 0, 1. At the next clock pulse, the LSB output would shift into the next flip-flop. The first flip-flop, that is, the first flip-flop will go to the second flip-flop, and second flip-flop will go to the third flip-flop. Output of the third flip-flop goes back to the LSB flip-flop. Hence, at the second clock pulse, the Q3, Q2, Q1, Q0 output would read as 0, 0, 1, 0. The LSB has become 0 because it has taken the input from Q3, and the output at Q0 has moved in to the J1K through the input of the next flip-flop to its output. Of course, after a certain delay of few nanoseconds. That is known as the propagation delay, as we have studied in our earlier lectures. So third clock pulse will also read as Q3, Q2, Q1, Q0 would be equal to 0, 1, 0, 0. Fourth clock pulse would have Q3, Q2, Q1, Q0 as 1, 0, 0, 0. At the fifth clock pulse, again the ring would be completed, and Q3, Q2, Q1, Q0 would read as 0, 0, 0, 1, and the cycle repeats. Now, what are the uses of these ring counters? Ring counters, of course, we have understood how it is just moving from one bit to the next and shifting. Basically, it's a shift left register, and the data case, only the 1, is moving from right to left as we see on the screen. Now, when the clear goes low and then back to high, the initial output word, as we have discussed, goes out as Q3, Q2, Q1, Q0 is 0010 after we have put in the 1. So, what are the applications of this ring counters? Applications of these ring counters happen to be the cases where we have to address a particular memory site. For example, take the case of a lift. In a lift, we have to go to a particular floor. When we go to a particular floor, we press the floor button. When we press the floor button, at the user interface, we say, let's say, we stay at 11th floor. So I press the button 11. But what actually happens behind the circuit is that the 11 is converted into digital equivalent. That digital equivalent is set as 1. The 11th floor is set as 1. All other floors are set to 0, and the lift moves from the ground floor, assuming we are entering from the ground floor or from the basement, we go to the 11th floor. So, the ring counter actually stores the 1 bit which follows a circular path moving left through the flip-flops until the final flip-flop, and it comes back to its original flip-flop. This completes the total ring. By adding more and more flip-flops, we can get hold of a bigger word simply by converting the data value that we require into number of flip-flops that we already have discussed in our previous classes. So, this diagram here actually summarizes the movement of the single bit, and we see that initially the Q0 was 1, and later after 5 cycles also it turns out to be 1, because in this case we have 4 flip-flops. So, as we discussed, we have several devices which actually use ring counters to keep track of the memory spaces wherein we need to address or send a particular bit. So, there are also other counters which, by changing their design, take help of ring counters to keep a track of how many states have passed by. A typical counter that we use in our day-to-day lives is the mod 10 counter or decade counter. So, as we know that since we have to simulate the decimal numbers, or we have to simulate the decimal counting using this counter, hence we have taken the help of 4 flip-flops. Decimal numbers start from 0 and take up 1, 2, 3, 4, 5, 6, 7, 8, 9. Then they reset to 0. Rather, what number we call as 10 is moving into 2 bits. Hence, we at the minimum we have to take 4 bits, and for 4 bits we have to take 4 flip-flops. It is important to note here that 4 flip-flops can give us 2 to the power 4 states, that is 0 to 15. In decimal terminology, they will count, or they can help us count, 4 bits can help us count from 0 to 15. 0 to 15 are actually 16 states, since 0 is also a state. Looking at the circuit, we see that it can count from 0 to 15. However, we have to arrange certain mechanism which will help us, or which has to help us, stop this circuit from counting after 10th state. That is, this circuit should be made to count from 0 to 9 and then reset itself to 0, 0, 0, 0. That is, 10 states are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it has to reset. 0 to 9 are 10 states. We cannot have a 10, 11, 12, 13, 14, 15. Right? So we look at the circuit. When we look at the circuit, we see certain aspects, like there are 4 bits, that is 4 flip-flops. Yes. This circuit, is this circuit a synchronous combination or asynchronous combination? This is asynchronous combination, as the flip-flop, each flip-flop is triggered from the previous flip-flop. That is, the clock is connected to its previous output of the previous flip-flop. In this, we have the high signal. So we understand that till the time we have the high signal at 0, then this will only behave, the circuit will again behave as a memory element and will not be counting. The moment high goes 1 or high goes high, then J and K values are 1, 1, and this circuit is now ready to count. We have again a clear, active low clear signal that is connected to an AND gate, and we find that till the time the output of the AND gate is 0, the counters will always be cleared. That is, it will always go back to 0, 0, 0, 0. Now, when the first clock edge comes, we change the state. When it starts counting, it changes the state, and we have the output from Q3, Q2, Q1, Q0 from 0, 0, 0, 0. It changes its state to 0, 0, 0, 1. Likewise, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, and the state keeps on going till the time we reach 1, 0, 0, 1. That is, Q3, Q2, Q1, Q0 become equal to 1, 0, 0, 1. At that point of time, if we look carefully, we have one NAND gate at the bottom, and it has 2 inputs, and the 2 inputs are coming from Q3 and Q1. So when we reach Q3, Q2, Q1, Q0 as 1, 0, 0, 1, the next state should be 1, 0, 1, 0. At that moment, the NAND gate values goes 0. The NAND gate is at the bottom of the page, and we see that the moment 1, 0, 1, 0 is generated, the output of the NAND gate goes 0. When the output of the NAND gate goes 0, it is connected to the input of the upper AND gate. Now, output of that AND gate also goes 0, and hence it clears out all the contents of the flip-flops, and hence the next clock pulse, after the 9th clock pulse, we have the output as Q3, Q2, Q1, Q0 as equal to 0, 0, 0, 0, and hence our counting stops. So with this method, we can define or design counter of any mod. We'll take up another case of a mod 5 counter, but I think here we have been successful in designing a mod 10 counter, despite having the mod capability to go up to mod 16. Mod 16 counter would count from 0 to 15, but herein, with intelligent use of output coupled to a NAND gate which acts as an input to an AND gate, we have been able to count or design this counter to count from 0 to 9 and then reset itself. So mod 10 counter we have been able to see that with the help of NAND gate and AND gate, we have been able to impart certain level of artificial intelligence into this circuit. So this herein is shown the decade counter timing diagram as we have discussed. So this we see is the negative edge triggered counter, and that whenever we have from the clock we have a falling edge, the output of the next flip-flop changes. For Q0, we see that every falling edge of the clock results in the change of state, and this keeps on going till we reach 1001. The moment we have the 10th clock pulse coming in for the output to change to 1010, the mod 10 counter resets itself to 0000. If you look at the mod 5 counter, the circuit is the same. Only thing is that it is expected to count from 0 to 4 and then reset itself. So herein we require the use of only 3 JK flip-flops, wherein it is designed naturally to count till mod 8, that is 2 to the power 3 is 8, that is it's a mod 8 counter, and it should count from 0 to 7 and then back to 0. But we have to reconfigure this to count only till 4 and then reset itself. Looking carefully at the diagram, we see that the first counting begins from 000, 001, 010, 011, 100. After 100 has 4 as its decimal equivalent, and therefore after this it has to reset itself. When it has to reset itself, then there should be some bit of artificial intelligence built into it so that it resets itself automatically. Using the same diagram as before, we have a NAND gate that output of the NAND gate acts as the input of the AND gate, which also has an active low clear. So in this case, what really happens is when we count from 000 to 100, that means for the next state, when we have 5 coming in, decimal 5 coming in, the circuit should reset itself. So in this case, as you can see, that the NAND gate has inputs from Q2 and Q0, and when both Q2 and Q0 go high, that is 101, then output of the NAND gate goes low, which acts, this low output of NAND gates is the input of the upper AND gate, and that upper AND gate goes low, and hence it clears out all the data from the flip-flops and it resets itself, the counter resets itself to 000. Hence Q2, Q1, Q0 begins from 000, passes, next state comes out as 001, then we have 010, 011, 100, and just after 100 it goes as again resets itself to 000. In this way, we are able to design any counter of any mod that we feel like. So as an exercise, it is advised to you students that you try to design counters of different mods. Maybe you can go for a mod 4 counter. For a mod 4 counter, you need to count from 0 to 3, and therein you will see that we require the use of only 2 flip-flops instead of 3 in this case. So changing mod just by 1, we are able to save the use of precious hardware, and only 2 flip-flops can be used. Thank you so much for attending to this lecture. We'll come back with a new lesson very soon.